I'm Hugo Larochelle. I'm the lead of Google Brain in Montreal. I'm also an adjunct professor at the University of Montreal. Cool. Looks like people are hearing me, so that's great. And yeah, I want to thank AI with the Best for inviting me to give a talk. I think it's great having an online conference like that. I think it's really cool, and there should be more. And yeah, so I guess today what I'll do is talk a bit about few-shot learning using meta-learning. So with that, let's get started. So yeah, I should say this is work that actually I've mostly done when I was at Twitter, but I'm still very interested in that problem. I think it's an important one, which is why I thought it'd be interesting to discuss it with you guys today. So the one problem to keep in mind as I'm talking is this one here, where what we want to do is design a learning algorithm where I can take a very small training set, like this one, where there are 5 classes, but only one example per class. And what I want is a learning algorithm that will produce a learner, a classifier in this case, say a convolutional neural network, that will be able to successfully classify new instances from these classes, like this lion here, which is, I guess, class 4, or this bull here, which is class 5. And so that's the problem we'll be tackling specifically and discussing most in this talk. So in the context of the research that I've been doing and others have been doing, I guess this falls in this research agenda of just, first of all, taking into account the fact that a lot of the deep learning successes we've seen so far has been enabled by the fact that there are large quantities of training data for, say, speech recognition, where there's been breakthroughs, or object recognition, or machine translation. And, well, the problem is that for solving these problems, we have to collect so much data, and collecting all of that labeled data required a lot of human labor. And I think that this is probably not how we'll be able to move forward towards an AI that solves many other tasks that requiring that we collect millions of examples for each individual ability that we think an AI should have is probably unrealistic. Or at least we should investigate other ways of approaching that problem. And so one alternative is to try to exploit other sources of data. And in some of the research that I've done in the past, I've been interested in trying to exploit unlabeled data, so that would be unsupervised learning, or multimodal data, so multimodal learning, where we have images and text. But here in this talk, I'll focus, and you should think of this work as falling in the domain of exploiting multi-domain data using transfer learning. So trying to explore the regularities between many different problems that each might have very little data, but between themselves constitute a large data set to learn from. And so the idea is that we will try to attack this problem very directly, this problem of few-shot learning, which is this problem of generalizing from little amounts of data. So specifically, what we want is to somehow design a learning algorithm, which I'll note as A, so that it outputs good parameters data for some model M. So for image classification, this model would be, say, a convolutional neural network, when it is fed a small training set. So one where we have X and Y pairs, and we have T such pairs, capital T, but capital T is very small. So there are very few amounts of examples per class. And the main idea in what I'll present is that instead of trying to define what that learning algorithm is by hand and use our intuition as to what is the right algorithm for doing few-shot learning, we actually try to learn that algorithm in an end-to-end way. And that's why we call it learning to learn, or as I like to call it, meta-learning. Let's go over a bit of notation. So if we go back at our definition, basic definition of what a learning algorithm is, well, its input, we'll define it by its input, its output, and what we're trying to achieve with a learning algorithm. Its input would be a training set. So it would be a bunch of X and Y pairs. Here I'm using capital letters because often we'll actually put these examples into mini batches. And we want the learning algorithm to output a model or a learner, or perhaps more precisely, we wanted to output the parameters for a model class. So say if the learner is a convolutional neural network, a good learning algorithm for a convolutional neural network would be one that would output the parameters of that convolutional neural network. So the filters and the biases and maybe the fully connected connections if it has some at the top. And a good learning algorithm is one that will produce parameters for that model such that the performance of that model on new example, on say a test set of a new batch of inputs and outputs, targets, has good performance. Okay, so that's really what makes what we qualify as a successful learning algorithm. It actually produces a model that generalizes well on new examples, not on the examples in the training set only. And so a meta learning algorithm, well, it will actually take as input a meta training set. And a meta training set here will mean many pairs of training sets and test sets, many examples of learning problems that we would like to have a learning algorithm successful on. Okay, so that will be our meta training set. And a meta learning algorithm would have parameters, so it would produce parameters, and now it's not parameters for a learner, but parameters for a meta learner. That is parameters for a learning procedure that takes, a training set and produces a model for that training set. And a good meta learning algorithm will be one such that if you run this meta learning algorithm on an example problem in a meta test set, or a learning problem you've never seen before, well, in that case, that would be another problem that has its own training set that is different from the training sets we've seen before, and a corresponding test set that's different. So a good meta learning algorithm would produce, would be such that if you fed it the training set, it would train a good model for that corresponding test set. So let me make that a bit more concrete. So if we take our problem here, so what we would like is to produce a good learning algorithm that takes the training set and will produce a model that I can apply in the test set and that performs well. So in meta learning, when we're trying to learn this procedure that takes a training set and produces a model, what we'll try to do is actually have a bunch of similar problems that will collect into a meta training set. So a bunch of other similar problems. So in this case, because we're interested in few-shot learning, these similar problems would be other problems with different training sets, but where the training sets all have a small number of examples, and they come with their corresponding test set. And also the classes within these other examples of training problems in our meta training set will not necessarily match the classes that we'll see in the problems in our meta test set, so the one with the lion and the bull, for instance. So specifically in the way we'll construct our experiments, in the meta training set, we will have images that are all from other classes than the classes that we'll actually see in the meta test set. And more concretely, the way we actually do this is that we will say take ImageNet, and then we'll pick, say, 64 classes for sampling problems for our meta training set. We'll pick another set of, say, 20 classes for the problems that will be in our meta test set. And those classes will be different. And so if I have lion here, I won't have any images of lion there. And the way we will be sampling these problems if we use ImageNet is that essentially we will pick a random subset of, say, 5 classes from the meta training set set of classes. So I said 64 classes. So from these 64 classes I chose. And then, so I pick a subset of 5 classes. And from each of these classes, I will sample a training set by sampling just one random image from each of these classes, or maybe 5. So we'll consider 1-shot and 5-shot learning. And then I'll sample other images for the test set from these classes, which I want, when I feed that corresponding training set to my meta learner, I want it to produce a model that works well on the test set. And so when we'll be meta learning, when we'll be training our meta learning procedure, what we will do effectively is that we will take, say, the first trained test set. So often in the parlance of meta learning, we'll call that an episode, train and test set pair, we'll call that an episode. So we will take the first training set in my first episode, I will feed it to my meta learner. So I haven't described you exactly what that is, and there are multiple examples which I'll cover, and I'll specifically start by covering my own work. So I'll feed the training set to the meta learner. Using that training set, the meta learner will produce a learner. So that learner, in the case that I'll cover, will be a convolutional neural network. The meta-learner will be something different. It will be like a recurrent neural network. The learner itself for these image classification problems will be something that takes one single images and produces a label. So a convolutional neural network is a natural choice. And then this learner, I will look at what is its performance on the test set by feeding each individual image here to my produced learner and looking at the loss. And in meta-learning, we're trying to optimize this whole pipeline so that essentially we have a way of changing my learning algorithm, changing the meta-learner, the way it produces classifiers for a given training set. So I'll do one update, and then I'll move to the next episode, the next example of a few-shot learning problem with its own small training set from different classes and its corresponding test set. So I'll feed that to my meta-learner, which has new parameters or meta-parameters, and we'll produce a new learner for that problem, and it will be evaluated on the corresponding test set, which will be evaluated using a loss, and I'll try to backpropagate all the way into my meta-learner to change its parameters. And I'll move over all the episodes like this, all of these few-shot learning problems in my meta-training set, and to evaluate the quality of my meta-learner, of my learning algorithm, I will actually feed it a training set from the meta test set, ultimately, which corresponds to new learning problems it's never seen using classes it's never seen. And that's how you essentially evaluate the generalization performance of a meta-learning procedure. All right. So now the question is, okay, how do I parameterize this meta-learning model? Okay. Well, so there are many things we could do. One of the things we could do is to take inspiration for currently successful learning algorithms. So an example of a successful learning algorithm, one that is used a whole lot, is to actually use gradient descent. So stochastic gradient descent is one of the most successful ways of taking a learner and fitting it to some data. And the way that works, as most people probably know, is that you take the current value of the parameters, and then you look at what is the loss for my model on the current mini batch, used based on the current value of the parameters, and then you take a step in the opposite direction of that gradient of the loss with respect to these parameters, multiplied by some learning rate, which might be based on RMS prop or some other learning rate schedule or adaptive learning rate scheme. And that gives me my new parameter, right? And so in this first piece of work that I'm talking about, which is this work I did with Sachin Ravi, who was my intern at Twitter, and did some great work here, is that this equation here is somewhat similar to a model that we know well, which is the LSTM model, a recurrent neural network where there's a cell state. And the way we update the cell state is that we take the previous cell state, we multiply it by some forget gate, and then we add to it a cell state update, C tilde, and which will be multiplied by some input gate. And now the thing that we essentially notice is that, well, if we make CT as large as the number of parameters in my model, essentially. And so if we make CT actually any parameter in my model, if we make C tilde T be the gradient of the loss for that parameter, and if we actually the negative gradient of the loss with respect to the parameter, and then we can think of IT to match this equation here as being a learning rate. And we can even think of the forget gate as essentially shrinking the previous value of my parameters, which is now corresponding to CT minus 1, shrinking it towards 0, which is a kind of regularization. And so our thought was maybe we can actually open up the parameterization of how to update parameters by taking inspiration from the LSTM, by having this forget gate, which is kind of acting like a regularizer, and this input gate, which will essentially scale to what extent I move in the direction of the gradient for each parameter. And then we need a way of parameterizing the forget and input gate, and LSTM essentially suggesting that the input and the forget gate should just be a sigmoid of some linear transformation of some information about the trajectory I'm trying to model. And in this case, what we'll use is that we'll try to make the learning rate, which is corresponding to this input gate, be a function of what is the gradient of the loss with respect to the parameter. So that means, if, for instance, the input gate noticed that the gradient became very small, it might determine that it makes sense to increase the learning rate automatically. It could look at the loss, which might be useful to identify when it's starting to overfit if the loss is too small on the training examples. It could look at the value of the parameters. Maybe, for instance, the parameters aren't behaving so well, or it might be able to detect certain divergences if the parameters became too large. And it will look at the previous input gate, so kind of like looking at what was my previous learning rate and whether that should impact my new learning rate. And we'll do the same thing for the forget gate. We'll also make it dependent on the gradient on the current parameter, the loss, the value of the parameter, and the previous forget gate. Okay, so that's one way of parameterizing a learning algorithm, of having a meta-learning model. And that's one way where we export, which we'll look at. So to be a bit more concrete, say I have one episode, so I have one small training set of, say, 1 image per class or 5 images per class, and I have its corresponding test set. This is part of my meta training set, so I'll do, what I want to do here is update my meta learner, so update my meta LSTM. Well, the procedure, the forward pass for that episode will be, well, first, let's start by an initial value of the parameters of my learner. So again, my learner will be convolutional neural net, my M model. And then given these initial parameters, I'll look at, for this current mini batch, this training mini batch X1, Y1, what is the loss and what is the gradient of the loss with respect to my parameters at their value theta 0. So I feed that to my meta learner, which I'm noting R. That will be my meta learning LSTM. And my meta learning LSTM will apply the update that I just saw here. So we'll take the current value of the parameters multiplied by forget gate, and then add the input gate times the negative gradient on the parameters. And it will produce a new suggestion for what the parameter should be, which I'm noting theta 1. So that's essentially the cell state value of my meta learning LSTM. So with this new value for theta 1, I will look at what is the next mini batch inputs and targets. And for the new value of the parameters of my learner, my convolutional neural net, I will get a new loss and a new gradient. And my meta learning LSTM, which is taking the current value of the parameters, will combine that information with the gradients and the loss for the current value of the parameters. And then it will produce a new proposal for what is the, it will essentially do a forward pass to get a new value for the parameters of the learner, the convolutional neural net. And then you repeat this a certain number of times, so calling capital T times. So in this case, I'm repeating it. In our experiments, I think we used 12 steps, and we fixed it to 12 steps. And then I can evaluate, okay, well, after having done 12 updates, essentially, of the learner parameters using my meta learner, what is now the performance when I look at the test set examples, X and their corresponding labels, Y? So I can look at what is the loss for my model when I feed it, and that's a typo here, when I feed it the parameters produced by my meta learner, and feeding it the inputs in my test set and their corresponding targets. And now meta learning will actually try to minimize this, minimize the loss of the produced learner on the test set. So that means we're effectively directly trying to optimize what is the generalization performance of the models produced by my meta learner. And because this is effectively essentially just a recurrent neural network, I can actually use backpropagation through time in order to update all the parameters within my meta learner, the parameters within the forget gate and the input gate. And another thing we can also train is the initial value at which I started meta learning. So the initial value of my convolutional neural network, which is like the initial value of the cell state, I can also do gradient descent on this and always start from this learned initialization. So another way to think of this is that what we're trying to do here is we're end-to-end learning and initialization followed by a fine-tuning procedure on a new problem in the corresponding episode. And we're training both the initialization and the fine-tuning procedure in an end-to-end way. And we're training it so that we have good performance on a test set. Okay, so to sum up, we're using our meta learning LSTM to model the parameter dynamics of my learner when it's training. So one way of thinking about this is that our learner M, say it has only 10 parameters, which is unrealistic, but say it has only 10 parameters, what we'll actually do is we'll have an LSTM working along these 10 dimensions. Along each of these 10 parameters, it will essentially have a cell state dimension for it, modeling how the parameter changes as it's going over and over all the examples in the training set. And we're using the same LSTM parameters across all the parameters. So it's kind of like, if I have 10 parameters, it's kind of like feeding to an LSTM and mini batch of size 10. But of course, in a ConvNet, we'll have, more than, that we'll have thousands of parameters. So it effectively is like feeding a very, very large mini batch into an LSTM model. And as I mentioned, we're going to also do gradient descent on the initial value of the parameters, which is the initial value of the cell state. So it is trained, as I said, to produce good parameters that have low loss on the test set for the corresponding problem, the corresponding episode. And it's possible to do this thanks to backprop through time. We do ignore the gradients, go through the fact that it's using the gradient on the parameters of the loss on the parameters. That is also a function on the previous updates that we did, and we're blocking those gradients. Now, I don't want to go into the details of this because that's a bit hairy, but you can see a discussion about this in the corresponding paper that we published at iClear in 2017. Also, the inputs of the meta-learning LSTM, as I said, is the loss, the parameter that we're modeling the learning of, and the gradient on the loss. And one thing that we did is that we looked at a particular type of preprocessing of the gradient, which provided some stability. And that was actually taken from this paper from DeepMind on learning to learn by gradient descent by gradient descent. And finally, I should say that in our experiments, our model M, which is a convolutional neural net, actually uses batch normalization. But you have to be careful to make sure that when you're using batch normalization and you're, say, evaluating on some, when you're collecting statistics, you want to make sure that you're not cheating by collecting statistics on the test set when you're doing evaluation, or on the validation set, in fact, or meta validation set with other episodes. And I don't want to discuss this more. I prefer talking about related work, but you can see a discussion about this also in our paper. Okay. So I want to say a few words about related work. So this work, we published it at iClear earlier this year. Since then, there's been a lot of other work, which is super interesting. So I want to make sure I cover that. I also want to start by mentioning that the idea of learning, of doing meta learning or learning to learn isn't new in itself. So meta learning is a class of methods for learning learning algorithm. And in this work that I'm talking about here, I'm talking about applying it to few shot learning, but you can apply it to other things. So I'm sort of showing you some references here which you might want to look at. So as early as in the 90s, there has been work on try to learn and update rule, which is somewhat close to what we're doing here, since the meta learner LSTM is effectively learning how to combine the gradient on the parameter with the previous value of that parameter, and it's controlling that with the forget and input gates. Here they had other ways in this previous work by Semi Benjo and Yashram Benjo and others, and just like Coutier, on trying to learn that update rule, or a different update rule than regular gradient descent. So that's kind of related. There's also been some early work on using RNNs that will modify the weights, not necessarily following a gradient descent procedure, but essentially producing weights for another model. And I won't go over that, but there's some work as well here that you might want to check out. And there's some other references in the Learning to Learn by Gradient Descent paper from DeepMind, which you might want to check out. So this is, I should mention also, in fact, this work. So in the Learning to Learn by Gradient Descent from DeepMind, the idea here, and perhaps the biggest difference with the work on few shot learning, is that they weren't interested in few shot learning. They were interested in learning an optimizer that works really well on many different architectures on large data sets. So there were a lot of scalability issues that they had to address. They also proposed this pre-processing of the gradient that we've also been exploiting. But instead of tackling the task of deriving a procedure that generalizes well in a small data regime, it's closer in this work here of producing a learner that learns faster than, say, Adam or RMS prop on the large data set. That's kind of the difference with this, but it's very interesting work. And one thing it does is that while it feeds into the optimizer, which is the meta learner in our notation that I've been presenting, instead of proposing essentially for input gates that scale the learning rate, that scale the gradients on the parameters, it's actually directly proposing an update on the parameters, which might not follow the gradient. It might not be it might not have a positive angle with the gradient for the mini batch. So it might learn something very different from gradient descent, in fact. Okay. But in the specific case of few-shot learning, there are a few pieces of work that I want to mention. One inspiration for our work was this work by Oriol Vignoles and others at DeepMind on matching networks. So the way to think about it in the context of meta learning for few-shot learning is that instead of having a meta learning model that is essentially initialize the parameters and do a few gradient updates, instead the meta learning model is essentially a pattern matcher. So it's one that will take a test example from the test set in an episode, compare it with all the training example of the episode. So it's sort of doing, you can think of it as learning a metric, where when you do this comparison of the test set examples with all the training examples of the different classes, so in this illustration there are 4 classes, well, you essentially get a good metric in order to estimate a vote of each example along each of the 4 different classes. And then that produces essentially a distribution over what is the class of this test set example. And because all of the pairwise comparison of examples and so there's some complication here or some sophistication that I won't go into, but where there's a bidirectional STM that is going over the set of training examples to learn this metric that is useful. But essentially, because all of this forward pass is fully differentiable, you can, again, end-to-end learn this pattern matcher such that it produces a metric that generalizes well when you only have a handful of examples. So that's an interesting piece of work I encourage you to look at. And then they also proposed the mini-MICHNet data set, which I'll evaluate on. You also have this work on prototypical network. This was an archive in 2016, but it's going to appear soon at NIPS by Jake Snell, Kevin Swirsky, and Rich Semmel. So in prototypical networks, instead of having a pattern matcher, kind of meta learning model, you have a prototype extractor. So what it does is that if we have, say, a 5-shot classification problem with 5 classes, class 1, class 2, class 3, what it does there is that we're going to learn a neural net that takes each individual example, which are these dots here. Those are each inputs from the training set of an episode. And we're going to pass them through several layers of a neural network, which will learn an embedding of the examples. And then for each class, the prototype extractor will take the average of the embeddings for each class, producing a single point, which is this black point here. It's the average of the embedding of all of the training examples for each class individually. So that gives us here 3 prototypes. And then if we see a new test example, then we'll compare the test example with each prototype of each class as extracted from the training set in the episode. And the way this is done is by just looking at the squared Euclidean distance between the X input here, which is embedded and corresponds to an example in the test set, with the prototypes, which is the average embedding of the examples from each class. So you compute that Euclidean distance, you take the negative of that and you pass this through a softmax, and that will give us a distribution over the 5 classes, class 1, class 2, class 3. And then you try to minimize the cross entropy of that distribution, comparing with the real label of that test set example in my episode. And so here again, it's kind of like learning in an end-to-end way, a particular learning algorithm that just computes an embedding and averages for each class, and then uses that to classify new examples. But now we're training it in an end-to-end way such that the answer you get for a test set example is the right answer. It assigns high probability to the right class. So what it will tend to do is learn an embedding such that all the examples of the same class are close in the embedding space. So that's another approach. Now, the approach that I described with our meta learner LSTM is in this family I would sort of roughly qualify as training and initialization plus fine-tuning procedure. And there's another piece of work which I really like from Chelsea Finn, Peter Beal, and Sergey Levine at Berkeley. It was published at ICML this summer. It's a very similar idea to meta learning LSTM, but the main difference is that instead of using a meta learning LSTM to do the fine-tuning, they will just use a known procedure, let's say Atom or any other optimizer that we know and love. And so what it learns essentially is just an initialization such that if you do a few steps of updates from a known optimizer that you choose, well, for each episode, for one episode, you might reach this parameter here from the same initialization. And from another episode, you reach another parameter setting or another parameter setting for another episode for another set of classes. So it's trying to learn this initial value such that it will quickly using, say, Atom or some other optimizer, reach the parameters of a convnet that generalizes well for that particular episode. So it's kind of replacing the meta learning LSTM with something like Atom. It seems to work better than meta learning LSTM. At least they have better results than we reported in our iClear paper. So that's an interesting direction for this family of meta learner models, which correspond to learning initialization that is fine-tuned after, but in an end-to-end way. And then there's another approach to meta learning for few-shot learning, which I also find quite interesting, which is to essentially just learn some form of black box neural network that you can apply on sequences. And so in this case, the model that you will be running will have to figure out internally how to learn a good learning algorithm. So when we're essentially using a meta learner LSTM or using MAML in the previous example, we're kind of constraining the meta learning model to be close to learning algorithms that we know. But we might want to say, let's try to have our meta learner model a procedure that might not be something we might derive ourselves by hand. So one early example at ICML 2016 was to use a neural Turing machine to represent a learning algorithm. In this case, so you have a sort of RNN with some memory, and you would present to the RNN at each time step a given image, and then at the next time step, you would provide it with what was the label of the image you provided at a previous time step. And the way this RNN, this neural Turing machine, is trained is that it has to produce at each time step what is the actual class for the input image that it was provided. And the way it can learn is that at the next time step, it will actually get the answer. And so internally, in this case, the meta learner needs to learn how to match the label that it sees at the next time step with the previous input that it got, such that, say, in the test set, if it sees another image that is kind of similar to an image it has seen before, well, it can simply go into its memory, learn to match it to an example of the same class, and then know that this example in that was in class 2, and so learn to assign high probability to class 2. So that's one approach, and more recently, in a paper that is, I think, currently only on arXiv and hasn't been published at a conference, again from our friends at Berkeley, they suggested instead of using a neural Turing machine to use a convolutional neural network with dilated convolutions. So something sort of similar to some of the autoregressive networks used for speech, for instance, and other things. So in this case, again, you have a sequence of some image, and actually let's use this one, some image and the previous label that is fed into not a recurrent neural network, but instead a convolutional neural network, and is trying to produce at this corresponding time step the actual label of the image that was fed, and the actual label will only be provided next. And internally, it needs to figure out how to use that information to become a learning algorithm. So that's another approach I encourage you to look out. And that is a really intriguing approach where we're essentially not constraining the meta-learning model to look like a learning algorithm, like a pattern matcher or something that does gradient descent or extracts prototypes. We're just hoping that a almost black box neural net will figure out some way of being a learning algorithm. All right, so quickly some results. We used the mini ImageNet dataset, which was proposed by Arnold Vinol in the Matching Networks paper. So here we have a total of 100 classes, 64 are used for training, 16 for validation, and 20 for testing. And then we generate, as I mentioned earlier, we will generate small training sets by picking a random subset of 5 classes within, at training time, the 64 training classes. And then we generate randomly some images from these 5 classes to get the training set. And we do something similar for getting this test set. We used a fairly small convolutional neural network for our model M, on which we're learning to do gradient descent and we're learning to initialize. We're actually using a meta-learner LSTM that has 2 layers. So the first layer of the meta-learner will be a regular LSTM, and then the top layer will be this meta-learner LSTM where the latent state corresponds to the parameter space. And so we did some comparison with some baselines. The first one is we train a classifier CNN on all 64 classes like we normally do with a 64 output softmax. And then that gives us initialization. And then we just use some regular gradient descent, a few steps of gradient descent separately at inference time to try to solve the new problems in the meta test set. And that is not providing super great performance, which suggests that actually end-to-end learning, both the initialization and the way we fine-tune, is beneficial. We looked at one where we used this initialization jointly on the 64 classes to learn an embedding, essentially a way of representing input images. And then so we essentially scrap up the top softmax layer, and then we do nearest neighbor on the topmost hidden layer. And that works a bit better with decent results. These are the Matching Networks paper, which had been published at the time we did our work. And then our meta-learner, actually, these are, we reproduced these numbers because there was a small difference in the way we use mini ImageNet. We're getting much better result as reported than these 2 baselines. And then our meta-learner is doing about as well for 1-shot, but substantially better for 5-shot. That was good news. And I want to mention that since then, there's been other results from prototypical networks, which I mentioned, MAML, and also the temporal convolutional network that I just mentioned, which are actually doing better now than what we've reported. So there's been fairly fast progress in the past year. I should say that, so MAML is using the same number of parameters as meta-learner LSTM. Prototypical networks, I think, is using a slightly larger prototypical net. I think this is still interesting, but it's just, I think that, maybe the meta-learner matching network could have better results if we had tuned the number of parameters. And I think this, future research should start looking at that instead of fixing the number of parameters. And the temporal convolutional neural network, I don't think really matched the number of parameters either. So I think, to me, the takeaway message is all of these things seems to work fairly similarly. And it would be interesting to sort of do another experiment where we fine-tune the parameters of all of those. But all of these methods are interesting. And I think in terms of future work and future research, I think we should start considering how to move to more number of classes and more examples and see how all of these different approaches are able to be robust when we change the number of examples per episode and when we change the number of classes per episode. We don't really know right now, but that would be very interesting. Also exploring new ways of characterizing, having meta-learning models, so characterizing learning algorithms. I think there are other things than an RNN or a fine-tuning and initialization scheme or a pattern matching procedure that we could use. Applying this beyond supervised learning, so doing unsupervised learning, meta-learning, semi-supervised learning, active learning even. There's actually some work from Microsoft Maluba.icml on using meta-learning to learn to do active learning, which is really interesting. Maybe doing meta-learning on the meta-learner. I think this is unlikely to be scalable in the short term, but once we can learn a learning algorithm, why not also learn a meta-learning algorithm? That might be interesting. So I guess that's it for me. I think we have maybe a few minutes for questions, so I'll go back. Yeah, so hopefully someone was asking about the novelty. So the biggest point is that we were emphasizing how we're trying to fine-tune a gradient descent-based procedure effectively, specifically for small shot learning or few shot learning problems. And I think we've shown that if we just do something kind of approximate, which is pre-train a model and then do a few steps of fine-tuning, then just separately, not in an end-to-end way, that doesn't work as well. So I think this is, one of our contributions here, and the contributions of MAML as well. So let's see how to choose the size of the meta learner LSTM. So we have a meta validation set, which is other episodes from other classes, and you just try various values there and see what works well. I should say the meta learner LSTM cannot be too big because, as I mentioned, you can think of, when we're training this, it's like having a mini batch for an LSTM that is of the size of the total number of parameters in your learner, in your ConfNet. So that's a whole lot of, that's a very big mini batch that takes a lot of memory to store all of the trajectories and all the cell states for each of these parameters. So it can be super big. So let's see. Training a large data set, would that give better results? That's a very good question. So we did try using our meta learner LSTM on, at meta test time, feeding it larger training sets than what it has seen during training, during meta training. And it actually doesn't necessarily reach better results. It's almost embarrassing in a sense because we're trying to learn a learning algorithm, but the procedure we're learning actually doesn't necessarily work better with more training examples, which is the main thing that that makes learning algorithms useful. So I think there's still some research to be done on trying to see how do we train a learning algorithm such that it is able to generalize outside of the problems it sees, and specifically outside of problems with larger number of training examples than what it has seen at training time. And that's currently something that has not been explored a whole lot. Applying this to text classification. I don't think there is work on text classification. I think it is interesting. It could be that some of these methods I described don't work as well in text classification, and new methods need to be designed. And which one within prototypical network or matching network, or something like meta learner LSTM or MAML, or something like a recurrent neural net that has to learn a learning algorithm, which one works better in text classification is unknown, I would say, at this point. So I think this is definitely something that would be an interesting other direction for meta learning, for few shot learning. I got text again. Good questions, guys. That's great. Let's see. Is it possible to train on image but validate on text? That's a great question. I'm pretty sure right now it would not do super well. So one thing to notice is that when we're training this meta learner LSTM, it is assuming a particular model of a given size because we're training the initialization. So the learner that you're using has to be, in this case, at meta test time, the learner needs to be a convolutional neural net with the number of filters that you've trained your meta learner for. So the approach that I've described, that I spend the most time on my own work, wouldn't actually allow you to generalize from images to text. I don't think, and actually none of these methods really could. So the only one that could, I guess, is one that doesn't learn an initialization, but then maybe learns an update rule that might be inspired from Adam, but has a few more degrees of freedom or something like that. Then you aren't really learning to learn. Stephen Hart is saying that you're not really learning to learn. We're certainly trying, and it does generalize to certain types of problems. That is, it does generalize to new problems that, yes, have the same number of training examples, but have different classes, for instance. I'll be the first one to admit, and the reason I say this is because I want to encourage people to look at how we can address this issue. So we are performing a form of learning on new data sets that we've never seen before, but those aren't with other examples. But I think it's I'm the first one to admit it. There's still some work to be done there. Doing cross-modality meta learning, I think this is related to like learning on images and then text, I suppose. CNN was smaller than typical. Do we investigate the headroom of that class, on that model class. So I'm not sure what that means, but we haven't, I think I said that a bit at the end, we haven't tried to, we didn't play much with changing the number of layers of the CNN or the number of filters of the CNN. We were taking inspiration from the work from Aurel Vignoles, who was using a particular architecture for the CNN it was using. And because we wanted to sort of try to match the number of parameters. And that's why I emphasize at the end that some of the more recent work hasn't necessarily matched the number of parameters. So, you know, some of the little additional performance might be due to this. I think that's something we need to investigate. And I don't think this reduces the value of that work either. I think it's still interesting. So sort of revisiting that in that context would be useful. And I think it might be really cool to have a learning procedure that actually learns the number of layers, a number of filters that would be produced for each episode. And that's something that I don't know anyone has done. I'm not sure I know what neat algorithm is. If you want to paste the reference, I'll check it out. And these are regression tasks. So you might, JSMIM, you might want to look at MAML. So MAML has some toy experiments on regression and also some experiments in RL using this sort of learn initialization followed by fine-tuning approach. So you might want to check that out, the Chelsea Finn's paper. It's a great one. Have you tried anything else except LSTM for meta learning like GRUs, dynamic memory network? Great question. I don't think we did. I don't think we tried other things. Could be that the GRU is better. So to be clear, I think, you know, the meta learning LSTM uses its cell state to model parameters. So that's cell state, and it kind of makes sense to use the LSTM updates in this case because it is effectively kind of shrinking the current value of the parameter like L2 regularization would do, and then doing a grade instead. So that kind of makes sense. But for the layer below it, something like GRU, or who knows, maybe the updates of GRU actually make sense, and it's just not something we've ever really considered for a learning algorithm. But I think, yeah, those are interesting suggestions, and you know, if that worked better, I'd definitely like to know. Do we train only meta learner model or learner model this also? So the learner model is trained during, you know, quote unquote, trained during the forward pass of the meta learner model, but there are no parameters that aren't being reinitialized of the learner model at the next episode. So really the only effective parameters here are all in the meta learner model. We could have some parameters of the learner model that are kept consistent across all episodes, and you could think of things like slow weights of the learner model, and the meta learner model would provide fast weights. That's something that could be, you know, interesting to investigate. But mostly all the parameters here that are trained and that are sort of evaluated on the meta test set are all within the meta learner model conceptually. That's the initialization from which it starts producing parameters. The theta 0, if you think of it as the parameters model, or C0, if you think of it as the meta learner model. And the way it produces learning rates, essentially, it produces the forget and the input gates. Those are all within the meta learner conceptually. We did not use dropout. Are there some examples of reinforcement learning techniques being used in learning to learn setup? Yes, there are. So actually the MAML paper, so Chelsea Finn's paper, has that, some experiments in meta learning. I think there is a learning to reinforce learn. I think there are two papers very close, one from DeepMind and one from OpenAI. And I can't quite remember the titles. It's something like learning to reinforcement learn or something like that. So those do exist. I don't have the references in memory, but I think they're not too hard to find. Let's see. So could it be related to meta? Both machines, could they be related to meta learning? I'm not sure. I don't see how they would be, obviously, in an obvious way, but maybe they are. I just don't see how they are right now. Let's see, meta learner will be initialized once at the very beginning of all episodes. So the meta learner, yes, the meta learner itself is being initialized. It needs to initialize the parameters of the for get gate, the input gate, and the sort of initial value of its cell state is also initialized in some way. For this one, you can use, like the Gloro initialization or, something standard. But yes, those are initialized before you do any meta learning, before you go any of the training episodes. Okay, I can stick around. Let's see if there are other. Oh, well, thank you. Learning to reinforcement, learn. Someone pasted the reference, whoever asked for it. That was G. Dikov. And there's another one from OpenAI, which if someone finds it, can paste it. And let's see. Maybe I can wait. There are last minute questions. Those are great questions, guys. Okay, so in your example, the classes were the shapes of the objects. What if they were categories like cat, dog, lion, wolf? So 2 classes instead of 4. I'm not sure I would say that the classes were, I guess, shapes. So sometimes there would be episodes. Oh, let's see, tame versus wild. Okay, I gotcha. Would this still work? I don't see why it wouldn't work. I think, but you're getting into something which I think is very interesting. Investigating how much the meta training set needs to be diverse to be able to generalize to problems which have different types of classes. So for instance, and as you're saying, what if you constructed at meta test time a sort of meta class which has, which has like, a tame category, which would be images of both cats and dogs. I think it would still work fairly well. I mean, to be fair, the results we're achieving right now are not mind-blowing. I think we've never done a human evaluation on any of these problems. The particular, there were some from other related problems like OmniGlob dataset. For Mini-ImageNet, I don't know that anyone has ever looked at the performance there of humans. But so we're still far from human performance. I suspect there would be a degradation. So in that setting where you have like tame and wild as a class at meta test time, but that's not something anyone has really looked at. And I think that would be interesting. Again, this is another thing that, because meta learning isn't something that's been explored a whole lot, it's been explored since, at least the 90s, but there hasn't been a ton of papers. I think that it would be interesting to kind of see the ability of all of these algorithms I mentioned to generalize, beyond the types of episodes it sees at meta training time. We don't have a good grasp. I mentioned if the training set is larger, some of these methods don't generalize super well. But when the number of classes changes, I don't know of results that indicate whether it would still work or not. I think this just work that needs to be done. What additional techniques could be explored to enhance meta learning? So thanks you all guys, appreciate it. Let's see. I think if there are other types of RNNs that one might think of, I think exploring the type of meta learner that is not inspired from a learning algorithm, but might not be a neural Turing machine or might not be say a convolutional neural network. So if you can think of other things like that, I think that would be interesting. Maybe reinforcement learning can be useful in the context of meta learning, so using meta learning for reinforcement learning. I know that there's some work on related problems, such as trying to use reinforcement learning to infer a new architecture for a ConfNet. That's kind of related. It's not exactly in the sense that, in this case, they're not looking at few-shot learning. So it's still meta learning, but not applied. It's applied to architecture search as opposed to few-shot learning. But maybe for few-shot learning, reinforcement learning could be useful for certain types of models. So one direction is to think of other representations of learning algorithms that you could meta learn. And there might be other learning algorithms out there that we could try to use as a representation of a learning algorithm that we would parameterize in some way and meta learn on a bunch of episodes. So that's another sort of direction to take inspiration of what learning algorithms are currently in use, which is what we did here, but that's great in descent. Yes, it is one example that's used a whole lot, but there are other learning algorithms out there. So thank you, everyone. Hopefully you enjoyed the presentation. And yeah, I'm also on Twitter. So if you want to chat with me there, I'm at Hugo Larochelle. So it should be easy to find. Take care, everyone.